in this case, remember, our weak acids do not completely ionize. So a lot of them stay together. In fact, most of them stay together. So you cannot break that apart when you're writing that net ionic equation. So the only thing that's going to cancel out for us is our sodium ion. And then that is going to leave behind these negative charges here. All right, so the first question asks us to calculate the initial pH of the acid before the titration begins. And so essentially what we need to know is what is the concentration of the H3O plus. So how much of that hydrofluoric acid is breaking up into those H plus ions that then make our hydronium. So we have HF, it is interacting with our water, and it is going to make H3O plus when that hydrogen joins the water, and it is going to leave behind that F minus. So in order to figure this out, we will have to do an ice table because we need to know what is the equilibrium concentration of the hydronium ion. And our initial concentration of our HF, it says, is 0.15 molar. Water is not going to be included, and we don't have any ions to begin with. Then we are going to lose some amount of our acid. We will gain some amount of our hydronium and fluoride. And then our equilibrium concentrations are 0.15 minus X, X, and X. So now, in order to figure out what the concentration of H3O plus is at equilibrium, we will have to use our Ka equation. We are going to use Ka because we are making this hydronium. We would use Kb if we were making OH minus, so if we were doing a weak base, strong acid titration. So our Ka is equal to the concentration of the H3O plus times the concentration of the F minus over the concentration of the acid. Remember, our H3O plus and our F minus will always be equal as long as we have a monoprotic acid, so one hydrogen, because the H3O plus and F minus are created at the same time. So I'm going to plug in our values here. So our Ka from the problem was 6.8 times 10 to the negative fourth. And that is equal to X times X, which is X squared, over, for our concentration at equilibrium for HF, we are going to ignore the minus X because it's less than 5% ionization. And we're just going to use our 0.15. At this point, we will multiply both sides by 0.15. So times 0.15. And then we will take the square root of both sides in order to solve for X. And I will get an X is equal to 0.010 molar H3O plus. Now the question asked for the pH, and so I will need to take the negative log of that concentration. And I get a value of 2 for my pH. Model that, I would just have my HF, and so little of it ionizes, you can really keep it all together. You could make this one H plus and F minus if you want, just to show that some of it ionizes, but I am just going to keep them all together because that value is so tiny. All right, so the next point in the curve is we have added a little bit of our base. Okay, so now I have this hydrofluoric acid, it's reacting with my NaOH, and some of it is going to be neutralized. And so I will have to figure out how much of it is neutralized, how much of it I still have left over, and then what is the concentration of my conjugate as well, because it is going to hydrolyze. So I have the reaction will be HF plus NaOH. This is a one-way reaction because it is neutralizing, and I will make NaF and HOH, which is water. You could leave these out, these sodiums, if you wanted to, because they are spectator ions. All right, so I need to know how much of it reacted, how much of my acid reacted with this much base, so I will use an ICF table. Remember, these are in terms of moles, not molarity like our ice tables. That is a really important distinction and something you got to keep in mind. So I need to know how many moles of HF do I have initially. So in order to find moles, I will do liters times molarity. So 0.030 liters times 0.150 molar. And I have 0.0045 moles. So 0.0045 moles. My NaOH, I have 7.5 milliliters, so 0.0075 liters. And the molarity of my base was 0.3. So when I calculate that, I get 0.00225. And I initially have none of my conjugate. So I am going to react 0.00225. And I will create 0.00225. So all of the base is used up. I have 0.00225 moles of my fluorine, and let's see how much is left. I have 0.00225. Okay, so I have a buffer. I have a weak acid and I have its conjugate. And not only that, but I'm at the half equivalence point. And that happens when I've neutralized half of that weak acid. So whenever those concentrations are the same, we can simplify the Henderson-Hasselbalch equation because we know at that point my pH is equal to the pKa. So I can take the negative log of that Ka, 6.8 times 10 to the negative fourth, and I get a pH of 3.17. At half equivalence, I have neutralized half of my acid, of my original acid. So I should see like 2 of my acids still together, and then I've put in enough of my NaOH. My NAs I see, my OH has joined with the hydrogen from the hydrogen fluoride to make water. We're not going to model that. And then we still have my F minus left over from the acid that we neutralized. So our acid is equal to the salt from the NaOH. Okay, so then we just keep going. Now we're adding a little bit more of our base. And we're going to start this one just like we did the last problem. So we have to figure out, well, how much did we neutralize? How much of my acid is left? How much of my base is left? And then how much of that salt is there? Because that salt will have its own acidity or basicity depending on the problem, if we're starting with a weak acid or a weak base. So we're going to start with our balanced equation again, HF plus NaOH. We are going to make NaF and HOH. We're not going to be including anything about that. Remember, this is in terms of moles. These starting values stay what they were, 0.0045, 0.0, oh, this one will change though. And we have none of my conjugate at the very beginning. So my NaOH now, I'm going to do liters times molarity again, but now I'm using a different amount of liters, 0.015 liters times the molarity of my base was 0.30. and I get 0.0045 moles. Notice they're equal, the acid and the base. That means I'm at equivalence. That means I have neutralized all of my acid. So I have no acid, I have no base, but I do have 0.0045 moles of basically the F minus, because the Na that's here we don't see in our final formula. All right, so in order to calculate pH, what I need to know, of course, is, well, what is the concentration of the H3O plus? How much of the OH minus is this basic salt, this conjugate base, is it going to make? And so I am going to have my conjugate base interacting with water, and the hydrogen is going to join with my fluorine and make hydrogen fluoride, and it's going to leave behind that OH minus. So I will have to do an ICE table in order to figure out the concentration of that OH minus and use that to find my H3O plus. Remember, this will be in terms of molarity. So my starting amount of my F minus is in moles. So before I can plug that value in, I need to find molarity of my F minus. So I have 0.0045 moles, and what I need to know is the total volume of the acid and the base. So I'm going to use this 15 milliliters of the base along with my starting volume of my acid, which was 30 milliliters. So 30 milliliters plus 15 milliliters is 45 milliliters, so 0.045 liters. And I get 0.10 molar. My water I will not include. And then from that, I have no HF and no OH minus at the beginning. I will lose some amount of my fluorine, gain some amount of these. And then my equilibrium concentration 0.10 minus X, X, X. So to figure out, well, what is the concentration of this OH minus so that I can then find H3O plus, I will need to set up the equilibrium for that. In this case, I'm going to use Kb because this is creating OH minus. So I can't use the Ka, I need to use Kb. So I will have Kb is equal to the concentration of HF times the concentration of OH minus over the concentration of F minus. I am going to ignore this minus X because my value is so tiny. All right, so Kb was not given to me. I do know that Ka times Kb is equal to 1 times 10 to the negative 14th. So I can divide off the Ka to find that Kb. So when I do 1 times 10 to the negative 14th divided by the 6.847 times 10 to the negative 11th. So I have 1.47 times 10 to the negative 11th is equal to x squared over 0.10. I multiply both sides by 0.1. Then I will take the square root, and I get x is equal to 1.21 times 10 to the negative 6th. And this is equal to the concentration of the OH minus. Now, there's several different ways I could go about it. From here, I'm just going to show you one of your options. I could take the negative log of this value. That will give me my POH, which is 5.91. Which is equal to 5.91. And then I take 14 minus 5.91, and I get a pH value of 8.08. At equivalence, I have the same amount of the spectator ion from my NaOH as I do the F minus. Okay, and then finally I have the end of the titration when I've added too much of my base, and then I wonder what the pH is then. So I'm starting with my acid. Again, I'm adding NaOH to it. I'm going to make some amount of NaF and water. I will do my ICF table. Again, this is in moles at the beginning. So HF at the beginning is the same as it was before, 0.0045 moles. My NaOH, I will do 0.020 liters times the molarity, which was 0.30 molar. And I get 0.006 moles. And I have none of my F minus at the beginning. So I'm going to use all of my acid, and I will still have leftover base. So I have no acid, 0.006 minus 0.0045. And I get 0.0015, 0.0045. All right, from this point, again, I'm trying to find the pH. The pH is really going to be dictated by the presence of this excess strong base, this OH. So I can actually calculate the POH from this concentration. Even though I do have a little bit of this conjugate base, the pH is coming really primarily from the OH from my NaOH because it is a strong base. Log of my OH minus concentration. And I don't have that yet because remember this is moles. So before I can plug that in, I need to divide by the total volume in order to get the molarity. So my total volume at this point, I have 20 milliliters of the base, and I started with, remember, 30 milliliters of the acids. That's a total of 50 milliliters. So 0.050 liters. So I get a molarity of 0.030 molar. So I'm going to take the negative log of 0.030. And I get 1.52. And 14 minus 1.52 will give me my pH, which is 12.48. Then I do want to model that. At this point, I have the same stuff that I had before, so I still have so at this point, I still have Na+. So I had 4, and now I've added an extra one. And I still have those F minuses. But I also have, because of this excess Na+, I also have now OH minus in solution, which is why my solution is basic.